This video is going to take you through the basics of the atomic model. You have an organizer that goes along with this video. It is page 203. So if you have not yet gotten that out, go ahead and pause the video, get out that organizer so that you can take notes on it, or use your own paper, it doesn't matter to me. After this video, you've got a couple of problem sets to do that goes that supports the practice with this. Now, with the amount of information that we have on this video, I'm going to have to break it up into a couple parts. Just so you know, it's all the same information, so you just got to watch a couple videos perhaps. All right, so we're taking a look at the atomic model. So a little bit of a review. Remember that atoms are what we consider the building blocks of matter. They are what everything is made out of. You can't break an atom down without losing all the properties that you recognize of atoms. At this point, we know that there are approximately 116. Actually, got to edit that. There's 118 different kinds of atoms that are known to man. Each of them, again, with their own properties. They are referred to as an element and, again, own set of properties. All right, so in terms of size, an atom is about 1 × 10⁻⁻10 meters. So that's 10 times smaller than a nanometer. That distance, that 10⁻⁻10, is actually called an angstrom. And that's on the organizer of the metric units that you need to know. And that's why I put it there, because atoms are angstroms in size. Notice, however, that the nucleus, which is represented by the red dot, is much, much smaller than the overall atom. 5 orders of magnitude smaller. So the nucleus, this is obviously not a to scale drawing. The nucleus is much, 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 much smaller than the atom. And then the rest of the atom is comprised of what we refer to as the electron cloud. So most of the atom is electron cloud, and just a very, very, very small percentage is the nucleus. All right, let's take a look at those parts a little bit. So let's focus on the nucleus first. And the nucleus is where you're going to find protons and neutrons. Do you remember these terms at all from 8th grade or 7th grade science? The nucleus, obviously, like we've just established, is very small. It's also very dense. So what does that mean? Since it's small in volume, it must be very heavy in mass. And that is true. Most of the mass of the atom you are going to find is in the nucleus. It's so dense, or there's so much mass there, it contains almost 100% of the mass. 99.94% of all the atom's mass is in the nucleus. But it occupies a very small percentage. Take a look at that. Very small percent of the atom's volume. And just an interesting note, I have a couple of those in this video. If a person were as dense as the nucleus, you would weigh 75 trillion tons. That is crazy. So the nucleus, very dense. So now switching gears to the electron cloud, kind of the opposite of what we've been looking at. The electron cloud contains the electrons, ergo the electron cloud. It has almost no mass, yet it fills virtually all the volume of the atom. Now I have the word fills in parentheses because most of the atom is actually just empty space. So obviously it's much larger than the nucleus, and therefore, because it's almost no mass, but yet most of the volume, it's very undense. Here's another nice example. If the atom were the size of a soccer field, the nucleus would be a little dot in the middle, about the size of a millimeter. That's the size of a ball bearing or a BB. And the electrons would be like a few little bits of dust swirling around the field. Like you can't even see the electrons compared to the nucleus itself, or even how big the whole atom is. But get this, this is the cool part. Those little pieces of dust would be moving so fast that you would not be able to walk onto the field. So that's what those electrons do. Those electrons are so fast moving that they keep anything else out of the electron cloud, which I think is a really cool visual. All right, so let's take a look at these protons, neutrons, and electrons. Atoms are comprised of these smaller particles. So what do we know about them? All right, well, hopefully you remember protons are positively charged, neutrons have no charge, and electrons have a -1 charge. Mass-wise, you might not have learned these numbers in grams, and I actually am not going to ask you to know them. Have them written down because occasionally we need to refer back to them for an example in a calculation, but you don't have to ever memorize the grams. What you do need to know is the mass in AMUs. Do you remember what AMU stands for? Atomic mass units. Instead of us having to remember a huge, or I should say a really small number, like 1.67 times 10 to the -24, scientists created a new mass unit, the atomic mass unit. So for protons and neutrons, they are essentially the same thing. So we give them an AMU of 1. Electrons, notice 10,000 times smaller, or I'm sorry, 1,000 times smaller, 4 decimal places smaller, which means that compared to a proton or a neutron, the electron weighs almost nothing. Okay, now, almost nothing, even though we write 0, please do realize that it has a little teeny mass. All right, so let's review the idea of the element. So an element is a set of atoms which has different characteristics from all other groups of atoms, all other elements. What makes them the same? The number of protons is actually what makes every element unique. So if you have an atom with 6 protons, you know exactly what kind of atom it is. If you have 2 atoms with differing protons, you have 2 different elements. You cannot change the number of protons without changing the identity of the element. So that's important to know. So protons defines the element. One way of sharing all the information about atoms is through a notation called isotopic notation. It is just a conventional way of showing proton, neutron, and electron information. So if X represents the symbol of the element, and there are no elements X, we've just made this generic, there are 3 numbers that you can possibly see in isotopic notation. One of them in the upper left is called A, the upper right is Q, and the lower left is Z. Z represents the atomic number, A represents the mass number, and Q represents the charge. So you may or may not see a charge in isotopic notation. If the atom doesn't have a charge, there's not going to be anything there. But in isotopic notation, you will always see these 2 numbers, the mass and the atomic numbers. All right, so what does that mean? If you look on our periodic table, there are 2 major numbers on any periodic table. There is a whole number, and then there is typically a decimal type number that is greater than the whole number, along with obviously the symbol. So how do we take this information and translate it into isotopic notation? Because if you remember, the periodic table is arranged according to this number. This number actually represents the atomic number. So it's telling you what number it is on the periodic table. And then this number, or a form of this number, represents the mass number. So it's arranged a little differently between a periodic table versus isotopic notation. The atomic number is always on the bottom left. The mass number is always on the upper right. So let's take a look at these different things. Let's look at the atomic number first. The atomic number is really equal to the number of protons, and that's why the periodic table is arranged by increasing atomic number. As you add more and more protons to the atom, you're making a different element. And so atomic number, or Z, is equal to the number of protons. There's one specific Z for each element. So if you know that Z is 11, you know you always have sodium, and you can look at the periodic table to verify that. If you have a Z of 26, it's iron. If you have bromine, the Z always has to be 35, and so on and so forth. So the number of the number of protons helps define the atomic number, and vice versa. If you know what the element is, you know what Z is. If you know what Z is, you know what the element is. All right, the next one we're going to take a look at is the mass number. Mass number is actually equal to the number of protons plus neutrons. And if you think about it, it makes sense because most of the mass comes from the nucleus. And what do you have in the nucleus? Protons and neutrons. So the mass number is really the mass of the nucleus, but the electrons are so tiny we don't really even count those. So to get the mass number, you have to add protons and neutrons together. Protons and neutrons. Z plus N. It's always going to be an integer. So when you look at the periodic table, you're not seeing mass number, you're seeing something else. Mass number is always a whole number because you can't have a fraction of a proton or a fraction of a neutron. You have to have whole parts. So as a result, when we talk about mass number, we can only talk about one atom at a time because atoms' masses can be different. So the mass number really only applies to an individual atom. And again, you cannot get the mass number from the periodic table. That's a really important point for you to know. So let's do an example. So I want to know how many protons and neutrons you have in this atom with the isotopic notation 23, 11, and Na. So you actually don't even need to look on the periodic table. You know that the number of protons is 11 because it's sodium and you're given the atomic number of 11. Neutrons must be 23 minus 11 or 12. All right, there are atoms of atoms of the same element which actually have different mass numbers. They are called isotopes. So how do they wind up with different mass numbers? Protons can't change. If it's the same element, the element number has to be the same. So therefore, what's got to be different? The number of neutrons. So here's an example of an isotope. Yeah, I got a little bored making the video. So you've got uranium-235 and uranium-238. Those are the two most common isotopes of uranium. So how many protons in each? Well, you look up uranium on the periodic table and you see the atomic number is 92. So 92 for both of them. But that means to get number of neutrons, you're going to have to take the mass number and subtract 92. So you've got 143 neutrons for uranium-235. This is, notice, U-235 is another way of indicating what the isotope is that you have. So the symbol followed by the mass number lets you know what isotope you're talking about. So therefore, uranium-238 has 3 more neutrons because the mass is 3 higher. Uranium-238 has 146 neutrons. All right, so I am going to stop here with this part of the video because I'm running out of my 15-minute time, and we're going to get into a new topic. So the new topic is atomic mass. We will pick that up in part 2 of our video.